Alright, we're back to learn you a Haskell. Yesterday we finished the type classes and we started touching on functions. Or the syntax in functions, so to speak. Yeah, type classes took a little while for it to get in, but now it's all there in the name, isn't it? They are classes that have different types in them, kinda. Yeah. Right, welcome back to the chat, Banana Wolf Monkey, yeah. Right. So we started doing with some pattern matching. We did trying this out yesterday, right? Yeah. And changing our type classes around. Right, when you... Oh, right, we did this as well. Wait, actually, let's continue reading from here. When you call lucky, the pattern will be checked from the top to the bottom. When it conforms to a pattern, the corresponding function body will be used. Oh yeah, we were talking. This is kind of like a. This is kind of like a loop, right? Where you loop over. You run it. If you get 7, else... Oh, it's an if-else statement, kinda. Yeah, this is an if-else, not a loop, per se, because it just goes over it once. But that's how you create a loop out of this syntax, is that you just do a recursive call, right? You could do... yeah, if you wanted a loop, right, where you checked for increasing numbers, you could call lucky x... No, suck x. Yeah. Lucky suck x. My favorite thing. And there you would have it. A recursive loop. But you would have to, right, that would be an infinite loop here, so... that wouldn't be a good idea. Classes suck. Exactly. My favorite function in Haskell, for sure. Alright, it checks from the top to the bottom. The only way a number can conform to the first pattern here is if it is 7. If it is not, it falls through the second pattern, which matches anything and binds it to x. Indeed. Ah. Oh, right, it binds it to x. Right. So if I call lucky 14... Actually, this needs to be scienced. Let's bring this not over here, but over here. Right. Right, we have this thing. A lot cleaner. Passes can't spell success without suck. Nice. Nice. Indeed you cannot. And Colgate Untitled added it as a quote to our list of quotes. Right. What was I gonna try? Shit, I lost track. Oh, right. So we kinda... do we have... like if I run lucky 8? No. So we load test. Oh shit. Right, I broke this thing, didn't I? Alright. Yeah. This is not the lucky things. So this time we're gonna write it a little bit faster than last time. Right. And now we load test. And we run lucky 14. And then we run x. No. Right? Because this sounds confusing. And binds it to x. I was kind of thinking that... Yeah, but the variable is not in scope. Yeah, because it just returns, right? If you want something like that, that's what I thought, right? You need to do this. X is equal to lucky 14, but then it doesn't become 14 either, because it becomes you're out of luck, pal. Yeah, you're out of luck, pal. We'll get in on tabs is learning Haskell. That was pretty fast typing, yeah. Nice. Functions don't have side effects. Exactly, yeah. So this language, what does this mean? Binds it to x? Oh, wait. If it not, it falls through to the second pattern, right? That makes a lot of sense. Right? We call it lucky 14. It comes over here, lucky 7. We did not call lucky 7. We called lucky x, which is an integral. Yeah. It is an integral. Therefore, sorry you are out of luck, pal. And if we try to call a float, it's just gonna say no. Yep, no floats. Cass says, why are frogs so... Cass asked for a joke, so here we go. Why are frogs so happy? They eat whatever bugs them. Alright. Colgate in tab says it means that if you have x on the other side of equals, it uses that as x. It means that you have x on the other side. Oh, right. So if we did... sorry, pal. Sorry, you're out of luck, pal. How do we do this? Oops. Like we could do... Was... show? The show output a string. Right. Reload. No? That didn't work. Alright, why not? Says, ha ha ha. Yeah. Funny joke, eh? Yes, show. Alright. Could not deduce. Oh, wait. Show A arising from the use of show from the context. Oh, right. Our definition. Wait. Where are we at? Doesn't this become one long string? Right? Isn't this the thing I've marked here, right? If we take, well, actually, if we do this, right? Type, and then we do hello world. Yeah, it's a string. So shouldn't this be a string as well? So I kind of misunderstood then, didn't I? Oops. From the context integral A. Yeah, it's bound for the type signature integral. Possible fix, add show A to the context of the type signature for A. Wait. So this is the problem, that it says it's an integral. It has to be... Right, so how do I do that? If I want to make sure it's a part of integral and it's a part of show. The type class, is there a way to do that? Like, can I just do integral show A? That doesn't work, does it? Oh, of course. Right, integral A, show A. Right, I was thinking A and B, but this is both of them. Of course, thank you, Colgate Untitled, yeah. So that, it should work like this. Yes. And now it works. Lucky 6. And there it is. I understood something, yeah. The only thing I didn't know was the syntax of what I wanted to do. But what I wanted to do, after you describe, right? It binds it to X for this function. Yeah. It matches anything and binds it to X within this function. Ooh, actually, just to double check, does it bind it just here? Or can we... No, it's a lazy language. I was thinking of adding something down here, but it's a lazy language, so no. Oh, actually, let's undo that. Says Colgate Untitled. Says that's interesting that it requires it. Yeah, right. It should have type inference and be able to figure this. No, right. Since we already decided it should be an integral, it will not do any type inference. I've already taken it upon myself to decide what types, what type class A is a member of. Yeah. So it shouldn't. Yeah. Try it without to. Yeah, like if we... actually, we can just comment this out, right? Is that how you comment in... How do you do a comment in Haskell? I don't remember. Pipeline and use T to see how Haskell interprets it. What is type line? Do you mean I should just do it all in here? Wait, didn't we do that already? Oh, you mean we can just do this? Isn't that what we did already? No, I'm confused. What are we looking for? Oh, wait. Right. Show. It's still the same, yeah. Oh, you mean we do the whole thing? Lucky X equal to... Damn, and then plus show 42. Oh, fill space. Yeah, that's what I was trying to do, right? I just needed to comment this out. That's what I was doing. But I need to comment this out. So I was asking, How do you make a comment in Haskell? Because I want to comment this line out. I don't remember. Right, I guess comment Haskell. Dash dash. Why doesn't everyone use the same type of comment? Right, and then... Right, and now we do T... what, lucky? Oh, right, yeah. Oh, that's interesting. Oh, yeah, yeah. Why didn't we have to do equality? Why is this here? We didn't write that. We just had to write integral and show. Is that some difference because it's an integral? All right, what if we do... integral and reload. Wait, is that not how you do it? Shit, no, that's not. Where do you put this? Oh, is it here? Integral, I don't remember. Syntax, not my strong suit. Nope. Oh, shit. Yeah, but I guess this here creates an EQ, but I don't remember if integral had to be EQ, so that's why. Oh well, it doesn't really matter. It's fine either way, right? There it is. Show and num. We had integral here instead of num, but can't do integral. Because integral is not a type, it's a type class. Yep. Yep. How many times have I made that mistake now? Probably 3 times since yesterday. And that same mistake will probably happen many, many more times. Yeah. Integral is not a type. Indeed. That mistake is gonna haunt me. You'll get there. Yeah, that's a mistake that I will do over and over and until I won't do it anymore. Easy mistake to make. Alright, where were we? Alright, we got stuck on bind to x. This function could have also been implemented by using an if statement, yeah. But what if we... Is he being facetious? Is that the word? But what if we wanted a function that says that the number from 1 to 5 and says not between 1 and 5 for any other number? Without pattern matching, we'd have to make a pretty convoluted if-else tree. However, with it... Yeah. And right, for this short a way of doing it, I remember we talked about this yesterday and I was considering finding a way to do, right, one function for all of these 5. And that's doable, but we're not doing that yet. Kaz says, you're doing a lot better than I, though. I mean, I've been doing this for a week now. Yeah. And we're moving at my pace. So yeah, I decide the pace, so it's easier for me definitely than it is for you in this situation. Yeah. Colgateino tabs is 3. Why 3? I would have always either picked 4 or 2 because I'm such a nerd. No, I'm a fanboy. That's what I am. It's a character flaw, isn't it? No, it's fine. Some numbers are better than other numbers. As a subjective value judgment. Colgateino tab says it's Mersenne prime. That sounds like math. Note that if we move the last pattern, the catch-all one... Yeah, the catch-all one to the top, it would always say not between 1 and 5 because it would catch all the numbers and they wouldn't have a chance to fall through and be checked for any other options. Yeah. That's usually how it works in programming. Remember the factorial function we implemented previously? This syntax is a little bit weird. It will take some getting used to, right? Like it's equivalent to the syntax in Python would be something like this, right? And then it would be just... Wait. Yeah, we have to make a convoluted tree. That's what happens, right? Right. If x is equal to 1, yeah, print 1, right? But instead of writing it out for all of them, we would just say if x is smaller than 5, print yes, else no, just to make my life easier. This would be the equivalent syntax, but we would have to do this 5 times over, yeah. No, actually, oh, sorry. That was older Python. Actually, it's not even that. It's not print, it's return. Yes, and return. No. Actually, no, this is not it either. We would have to, like, make a list and... No, that's fine. Yeah, return yes. Ooh, actually, we could just return... Yeah, we could do something like... it doesn't matter. We're not doing Python. I'm just saying that the syntax is... It's some other... Yeah, the syntax is different. This is like one function, but it's at the same time, it's 6 functions. It looks like you're writing 6 functions, but that's how Haskell works, I guess, yeah. A lot of tiny functions that combine into one bigger function or whatever. Cass says, did someone say maths? Starts having a stroke. Oh no, Cass. Right, repeat after me. Banana, waffle, and monkey. Sorry, that's what now that comes into my head, right? That's one of the stroke tests. Have someone repeat 3 unconnected words, but my mind just goes to those 3 words by now. Yeah. Colgateino tab says it's similar to switch in Java. I have not looked at Java like ever, so that doesn't help. unconnected. Exactly. Well, for you, or well, not for you, but right. You should take like a weekday, an animal, and I don't know, a food. Something like that. A stroke test. It's just to make sure that someone's brain is working as it should. Doesn't have to be that complicated, right? Yeah. Can they do this with their tongue? Right. If they can't, then they're having a stroke. Yeah. Remember the factorial function we implemented previously? No. We defined the factorial of a number... Oh, yes, I do remember this. We defined the factorial of a number n as a product of a list of all the numbers from 1 to n. We can also define a factorial function recursively. Here we go. The way it is usually defined in mathematics. Oh. Again with the maths. More maths. We start by saying that the factorial of 0 is 1. Is it though? Isn't the factorial of 0 0? It is, says Colgate on tap. How does that work? Isn't the factorial, right? We said that it's, yeah, it's, right? If you take the factorial of 3, it's 1 times 2 times 3. What's that, 6? Oh, right. For the factorial to work, we have to say that the factorial of 0 is 1. Otherwise, it would break the whole idea, wouldn't it? Because otherwise, all the factorials would be 0. And that the whole point of a factorial would get lost in an endless sea of zeros. Right. Then we state that the factorial of any positive integer is that integer multiplied by the factorial of its predecessor. Here is how that looks while like translated into Haskell terms. Right. Yeah, we take an integral and any integral and we get the same type. Yeah. We say that factorial 0 is equal to 1. All right, so this is set. 0 is equal to 1. Factorial n, call it, and then we just multiply it. Wait. N minus 1. Wait, why minus 1? Damn it, maths. Damn it, maths. Alright, so it starts out. And if we take... Oh, yeah, of course. We have to go minus 1 because we go back down to 0. Yeah, like if we call factorial 5 from the outside, for example, then it becomes 5 multiplied by 4 because we take n minus 1. And then we call it again times 3 times 2 times 1. What happens then? What happens? Right, we call it with 0. Wait, does an integral have to be positive? I don't think so, right? That can be a negative number. Yeah, ints and integers. Doesn't this create an infinite loop? Infinite recursion? Right, because factorial 0 is 1. That means that we call it with 1 again over and over and over and over and over and over and over. Hello, Mike Krafchik. Nice to see you again. How are you doing today? Do you know Haskell, by the way, Mike Krafchik? I haven't asked. Colgatinotab says you can think of n... Oh yeah, n exclamation mark as how many different orders there are for a list of n elements. Yep, with 0 elements there is only one order. Oh, I like that. Right, why does it stop? I suppose they explain it down here. With negative numbers it goes infinite. Yeah, and integrals can be negative, right? No? My craft chick says, I've never seen that language and I have a lazy Saturday. Oh, nice. Lazy Saturday. We're having a lazy language. Yeah, Haskell is a lazy language. I'm planning on having a lazy weekend as well. Right, let's read the following paragraph and maybe my question will get answered in a way that I can understand easily. Right, this is the first time we've defined a function recursively. It is, yeah. Recursion is important in Haskell and we'll take a closer look at it later. Oh, okay. I'm trying to get ahead of myself again, it seems. But in a nutshell, this is what happens if we try to get the factorial of, say, 3. It tries to compute 3 times the factorial of 2. The factorial of 2 is 2 times the factorial of 1. So for now we have 3 multiplied with the... Yeah, exactly. We get the factorial, yeah. The factorial 1 is factorial of 0, so we have... Exactly. This is what we have. And now here comes the trick. We've defined the factorial of 0 to be just 1, and because it encounters that pattern before the catch... Oh! It just returns 1. Right. That's what we learned before. This is the catch-all. That's part of the syntax, is that you put the... It's like the... yeah, it stops. Because Haskell is designed in such a way that everything always returns something, and if this is returned, it doesn't continue, right? It stops. And if we multiply it with 1 again, it doesn't matter, because multiplying stuff with 1 is pointless. It doesn't change anything. Right. That's how it works. We go down the list and we say, well, we did not go for 0, so we do this thing. Right? And then we do this thing again. And then we do the thing again. And one more time. Oh, now it's 0. So we end up here. And boom, we're done. We are done. Wait. It just returns 1? Doesn't this mean that when we call factorial, we get 1 every time? Right. So the final result is equivalent of all of this. Yeah, 1 multiplied with 1. No, it's because we call it down here. Yeah. Since we call it down here, it doesn't stop here, it stops here. It says that's why we get number 1 2 times. One time when it is the actual number, and then the second time when it's not, because it stops and it doesn't call anything else. It doesn't call this again, because it stops right here. I get it. Alright, so the final result, yep. had we written the second pattern on top of the first one, it would catch all numbers, including 0, and our calculations would never terminate. Yeah, that was my question exactly. That's why order is important when specifying patterns, and it is always best to specify the most specific ones first, and then the more general ones later. Okay. Pattern matching can also fail if we define a function like this. And this will throw an error, right? If it fails. Right, and then try to call it with an input that we didn't expect. This is what happens. Character A, B, H. Yeah. Throws an exception. Right. That's the same thing we do in Python, right? Instead of throwing... Yeah, we throw an exception that we can handle, right? Instead of just breaking our code, we just throw an exception that can be handled, which we will get to later, I guess. All right, now. Exception tut.hs. What a name, right? Non-exhaustive patterns in the function character name. Right. It complains that we have non-exhaustive patterns, and rightfully so. When making patterns, we should always include a catch-all pattern so our program doesn't crash if we get some unexpected input. Oh, we don't even have to handle an exception. What we do is that we just do what we did up here, right? We just put it in an X, like anything else. For anything else, do this. And our exception will be preempted rather than handled. Yeah. So we would just... Right, we would just add... we would just do like this. Our name X equal to what? None? I don't know. What do we look for? No, it has to be a string, so we just an empty string. Or something like this. Not available. Wonder if that breaks. I think that's the first time I've written something in this file and it has loaded immediately. Oh, right. I like that. Definitely like that. That's a good tip, calling it in on tap. Yeah, we just make an underscore. I think underscore instead of X would be more in line with generally used Haskell syntax, as we don't care about the value of X. Right, yeah. I really like that. Right? We should have done the same here. An underscore, right? That's an... Yeah, we don't care. It's whatever. Whatever. It doesn't... We don't care. So calling it X is... Yeah, I like that. I really like that. More descriptive. Right, so where were we? Pattern matching can also be used on tuples. What if we wanted to make a function that takes two vectors in 2D space that are in the forms of pairs and adds them together? To add together two vectors, we add their x components separately and then their y components separately. Here's how we would have done it if we didn't know about pattern matching, alright? We would add vectors. Yeah, we would take... yeah, they would have to be numbers. That's our type class. And we would have two of the same type right here. Yeah. Right? Just to double check, Colgate in on tap. These two have to be the same type. I can't have an integer and an int here, right? If I have an int here, there has to be an int here. That's why they both are a. If we had a and b, that is when we could have an int and an integer. Yes. Nice. Right. A is just like any type, but it has to be, we define here that it has to be a number. But since we have a and a, they all have to be the same type. So if one of them is an integer, all of them have to be integers. And we do type inference, right? Yeah. So if we have an integer, all of them will be integers. Yeah. Unless we try to, like, I'm just thinking whole numbers here, right? Ints and integers. All right, add vectors, A and B. We add them together. So we take the first from A and the first from B, and we take this. Oh, right, yeah. That makes a lot of sense, exactly. I haven't done a lot of vector math, but that is how it would work, right? Yeah, we add the x values and we add the y values. Looking good. Well, that works, but there is a better way to do it. Oh, is there? Let's modify the function so it uses pattern matching. Okay. We have the exact same setup. That makes sense. But instead... Oh. Yeah, that wasn't super clear here, but yeah, these are tuples. Pairs, to be exact. And this becomes way more readable. Yeah. I think this is preferable in so many ways. I find it to be easier to read, and we don't have to call first and second. Right, so my guess is that this would be more optimized, wouldn't it? Yeah, if we did this a million times and we did this a million times, this would probably be done quicker, I would guess. I don't know though, yeah. But yeah, I like this. Right, instead, right, so how do we try to remember to do things this way? Because just if I had to do this, if someone told me to do this, I would probably do it this way, rather than the pattern matching way. A general rule here would be to be more explicit, right? This is just more explicit. There we go, much better. Note that this is already a catch-all pattern. The type of add vectors in both cases is... right? So we are guaranteed to get two pairs as parameters. Yeah, when you work with tuples, that seems like that will always be the case, won't it? Tuples is restrictive like that. Right, first and second extract the components of pairs. But what about triples? Yeah, what about if we want to add vectors in three-dimensional space? Could we make a function like that? Well, there are no provided functions that do that, but we can make our own. Alright. First, oh right, we define Yeah, look at that. Wait. When we do... Oh, no, we gave it we gave it its own name. I was thinking, right, of this function. I was like, can we just replace? No, we gave it another name. Yeah. The okay name. I would probably name it first T3 or something like that for a tuple with 3 components. Yeah, second T3 maybe. Just to be extra clear. I don't know if we have to do that since, well, obviously there's a thing here. Right? Yep. And third, indeed. The underscore means the same thing as it does in list comprehensions. It means that we don't really care what that part is, so we just write an underscore. Which reminds me, you can also pattern match in list comprehensions. Check this out. Oh man, let's check this out. Alright. Let XS be a list of tuples. Yeah. And then we make a list comprehension where we take... Oh. Wait, I'm confused. Oh, right. We add the tuples together. That's what we do. I was still thinking about vectors, but this is like... And we stop doing vectors. Then we just add them together and create a list of... integrals. Now, create a list of integrals, right? Just thinking about types. Type classes. Right. Should a pattern match fail, it will just move on to the next element. Would it? Alright. Lists themselves can also be used in pattern matching. You can match with the empty list or any pattern that involves the single colon. Shit, I forgot what the single colon did. They are not necessarily integral. Yeah, they're not necessarily, but this list is. This is a list of integrals. But they are not necessarily, right? This thing can be... Right, we haven't defined any type. Wait, do they have to be numbers? I don't remember if plus had to be numbers. We can check that fairly easy. Oh. Probably nums, right? Actually, no, wait. Like this we check, right? Yeah, they have to be numbers. Necessarily they have to be numbers. They could be floats or doubles for all we know. Yes, exactly. Numbers. They have to be part of the num type class. This list comprehension, since we're using this plus, makes it type inference is that both A and B are of the type class num. They are members of the type class num. Right, but since 1, 2, 3 is just syntactic sugar for... Wait, can we do... prepend, right? That's a way to call this. This is a prepend to a list. Yeah, it takes something and a list of that something, and it prepends the something to the list of the, right? We have the list, we prepend 3, then we prepend 2 to that new list, and then we prepend 1 to that new list again. You can also use the former pattern. A pattern like x into xs. Colgate tab says colon is how lists are defined. Yeah. The list, this list is, yeah, like it says, it's actually this list. Oh, this is what a list looks like. But this is syntactic sugar to makes it easy. It makes it more human readable, or so they say. However, this here, right? This is how a list is defined. Well, that is how a list is defined, right? Right. Yeah. We can check for the type of this. Right? That's just a list of something. But this is how you define a list. And this is a function to putting things into the list, right? And it specifically prepends, doesn't it? Yeah, it puts it... Yeah, since it's lazy language, it's first it puts this in front of the list, then it puts this in front of the list, and then it puts this in front of the new list. So yeah, it's how it's defined with its contents, right? All right, so a pattern like x into xs, that's a list, and it puts x in front of the list. Yeah, will bind the head. Oh well, this is another way of looking at it. Yeah, it will bind the head of the list to x and the rest of the list to xs. I like that. Even if there is only one element, so xs ends up being an empty list. Yeah. Right, so one way of looking at it is that this is the tail, this is the head. New head into the new tail of the list. Right. Note that the x into xs pattern is used a lot, especially with recursive functions. But patterns that have colon in them only match against lists of length 1 or more. If you want to bind, say, the first 3 elements to variables and the rest of the list to another variable, you can use something like xyz into zs. It will only match against lists that have 3 elements or more. Wait. That's confusing. Wait, Colgate Innotabs says singleton to list. Element, not singleton. Makes sense. Wait, what are you talking about? Singleton? Element? Right, if you want to bind, yeah, the first 3 elements. This is just extra confusing, right? In this, ZS is already a list, right? And you can add these 3 elements to said list, right? The first 3 elements to variables and the rest. Wait, are we saying that it works both ways? That we could have, like, we have a list, and this could be an infinite list, and these are the 3 first items of said list. Yeah, that's what we have here. Yeah, because this is equivalent to, right? And then, right, the rest of the list could be whatever, right? Right. It's not this, right? Because it's not an infinite list, but doing it like this kind of you can define them as their own things. Alright. I guess we will get into that. It feels like these things will take more practice, right? Doing some actual coding for this to make sense to me, but I think it's fine, yeah. Colgate in on tab says, yeah, it could be. Alright, now that we know how to pattern match against a list, let's make our own implementation of the head function. Right. Our own implementation, it takes a list of something and it returns something. Right. And then we make a catch thing. Wait, error. Can't call head on an empty list dummy. Oh yeah, if someone tries to call it on an empty list, that's it. And then we take... Yeah, look at this. This is the head of the list, and the rest of the list we don't fucking care about. Yeah, I made like a dot thing before. Oh shit, it just disappeared, right? But this is it. Yeah, this would be the thing. The ZS we don't care about. Like, we don't care about the rest of the list. We only care about... Why do we have a parentheses here? Oh, right. We create a tuple. No, wait, what? No, why is there a... For style? Oh, it doesn't matter. Actually, let's actually try that. Is it just for style? Oops. Oh, what happened here? And we do need that. So we are creating a tuple then. Right, when we call head, or this one, when we call head on this and we take right, we create a tuple that looks like right, the in between, right, is a tuple that looks like this. Yeah. Yeah. No. Sorry. No, we're not. Yeah, it looks the same. You know what? For style, no syntactic reason. But when we did it without, it broke. Right? When I remove the parentheses from this thing, there's no syntactic reason. Why does it break? Parse error in pattern. No, it is order of operations. That's because we call head. Yeah. The colon is a function. So we have to have the parentheses for the order of operations. Because we call head on this resulting thing. Yeah. That's the syntactic reason. It's the order of operations. We have to call head on the result of this function. So we enclose this in parentheses to make sure that what we get out is in fact this. Since we have this thing contains two different functions, right? It's our function and it's the list. It's because of how lists work. Yeah, it's because of how lists work in Haskell. Try head and a $sign. And then, yeah, like this. Oh, actually, space here. If it's order of operations, that should also work. This looks a little bit like bash, doesn't it? No? Wait, but we did get some... We did get some error here, though. Precedence parsing error. Cannot mix main.$, infix, and in the same infix expression. This seems to be something else. The $sign seems to do something else that messes around with it. Right, but it works fine, yeah. It's fairly easy to make our own head function, though. All right, nice. Notice that if you want to bind several variables, even if one of them is just whatever, and doesn't actually bind at all, we have to surround them. Oh, here we go. We have to surround them in parentheses. Oh, so it's not an order of operations things. It's just pointing out that we do this on multiple variables. Okay. Also notice error function that we used. Oh yeah, we did. It takes a string and generates a runtime error. Oh. Using that string as information about what kind of error occurred. It causes the program to crash, so it's not good to use it too much, but calling head on an empty list doesn't make sense. Okay, let's make a trivial function that tells us some of the first elements in the list in inconvenient English form. Colgitone tab says, I forgot that. Yeah, I mean, there's so much information, right? All right, let's make a trivial function, yeah? Okay, so we take... It has to be a show type class, right? We take a list and return a string. All right, so tell, if we get an empty list, we return the list is empty, right? Then we take, if the list has one element, let's show, oh yeah, we show what element it is. The list has two elements, and the list is long. The first two elements are. Yeah, this all makes sense to me. This is a list with one element. This is a list with two elements. This is a list with... I don't know. I don't care. The list can be 3 elements. The list can be infinite. It doesn't matter. We only care about the 2 first elements. And these are the first 2 elements of our list. Yeah, so this, we could say that this helps us denote the end of the list when we write lists like this. Okay, this function is safe because it takes care of the empty list, a singleton list, a list with 2 elements, and a list with more than 2 elements. Yeah, exactly. This is the smallest list that is possible, and this works for the rest of the list. So this is safe because it has dealt with all the possible situations we can find ourselves in. Yeah. Note that note that this thing and this things could be written as, yeah, exactly. Because it's syntactic sugar, we don't need the parentheses. We can't rewrite this with square brackets because it matches any list of length 2 or more. Yeah, I made a mistake earlier when I did this thing. I did that thing because this is not equivalent. This is an infinite list. This can be an infinite list, but right, we don't even go that far. This, however, is definitely an infinite list. So yeah, that was a mistake I made earlier, worth pointing out. Right, with square brackets because it matches. Yeah, exactly. We already implemented our own length function using list comprehensions. Now we'll do it by using pattern matching and a little recursion. All right, we make our own length thing. Right, where b has to be a number. Why not an integral? Yeah, I would probably prefer to put this as a type class integral rather than a num. I guess when it compiles, it doesn't really matter. I guess the speed of compiling might be a little bit quicker if we use integral rather than num. But the actual, when we have our compiled finished program, I don't think it matters. Full tab says, so it can be used with floatings, but you can't use that. You can't get a float when you get the length of a list. You cannot get a float. Right, so you can? Wait. How can you get a list with a floating amount of elements? I don't see how... Right? If we count how long is this list, we can't say, like, we can't get 3.5 items. There are no... Like, that's... How long is that list? You can't get a float. How? Why? No, I'm confused. Alright. Length. Oh yeah, if we get an empty list, we get 0, yeah? And the length, we don't care. Okay, let's look at this. We don't care about... Alright, that's 0, but we get a list, and we care about the list, but we don't care about... I don't get why don't we care about what's before? We just care about the tail of the list, right? This is the... Right, and then we take 1 plus the length excess. Hmm. 4.0. This is called getting on tap. Oh. Yeah, I get it. Yeah, it can be used with floats. Yeah, if you want to do something with the result of the list. Yeah, if we want to do some division with the result of this function, then yeah, having num makes a lot of sense. Yeah, yep. I get it now. Thinking ahead, yeah. What do we do with the result of this function? We might want to use a float by then. Otherwise, we would have to call that other function, right? All right. So we call this, it takes a list, right? And does this lead to the last element of a list? Right, I don't know what this... Actually, let's take this thing. Let's remove all of this. I don't think we need any of this anymore. Boom. And then we copy this thing. Damn it. I don't... Right, and then we reload. And then we call length on a list of... Oops, that's not a list. Call it on this list. 69, 138. Did I? Oh. I was like, why isn't that working? That was... Yeah, we get 3. Oh. Yeah, it removes... Here we go. Yeah. This is the head. This is the first item of the list. Yeah, that is the head and that's the tail. That's what we talked about, right? So here we don't care about the head anymore. So we just take 1 plus, and then we do recursively. So the first time we call it, we have 1 plus the length of XS, which is the tail, right? So we call it again. And now the head is 69. So we have plus 1 more. That's 2. And then we call it again and boom, and then we're done because the next step, the length is 0, so we're done. Yeah, and I like that. That's a thing that I think I'm gonna make that mistake a couple of times as well. That, right, when I'm thinking is, what does this list return? Because my thinking is, I think of it as a loop. Right, so I think here is where it stops, but it's not. It stops after it has done the last plus here, because the last thing is that we plus 0. Because a function always returns something, we know that, right, when we call length, we know that we're going to return something, and we're going to return something on the other side of this side. So the first time we get 1, and then we get 2. Wait. Oh man. Takes some thinking to wrapping your head around the recursion. I thought I had a fair understanding of recursion, and I kind of understand how it works, but at the same time it's a little bit extra complicated. Because we don't give orders to the machine. Actually, yeah, this is functional programming, like a significant difference from imperative. Because in imperative, you always tell it to return something. But that command to return something is built in the whole structure of the thing. It's a function. Right, this is similar to the factorial function we wrote earlier. First we define the result of a known input, the empty list. Yeah. This is also known as the edge condition. I like that. Yeah, the edge condition, right? It's sooner or later we will, with this function, reach... Yeah, if we want to do something with all the components of a list, we will reach this we will reach this end. Yeah. Yeah. Then in the second pattern, we take the list apart by splitting it into a head and a tail. Exactly, yeah. We say that the length is equal to 1 plus the length of the tail, and then Yeah. We use the underscore to match the head because we don't actually care what it is. Also, note that we've taken care of all possible patterns of a list. The first pattern matches an empty list and the second one matches anything that isn't an empty list. It's not safe though, yeah. We have taken care of everything, but it's not completely safe because we don't have a top edge condition or whatever, right? If we feed an infinite list into this, it's never gonna stop recurring. Oh, nice. Yeah. We'll get in on tab writes that what we get is, right, if we write it as maths, I like that. This was a good way of looking at it. This maths is maths I understand. Exactly. Oh, shit. Sorry. There we go. Those are equivalent. Yeah. This, yeah, exactly. That and that is equivalent. Is that the word? Yeah, because they both result in 3, so yeah. Like, wait, it's not equivalent. Equivalent is not a word, because this would also be the thing, and we could do... They are equal? Shit, I don't know the lingo. This one makes sense, right? This is a good representation of what is going on. Right, and we can just continue this pattern for however long our list is. Let's see what happens if we call length on ham. And that's 3 as well, yeah. First it will check if it's an empty list, because it isn't. It falls through to the second pattern. It matches on the second pattern, and there it says that yeah, the length is 1 plus length of am, because we broke it into a head and tail and discarded the head. Okay, the length of m is 1 plus the length plus m. So now we have, yeah, here we go. 1 plus 1 of the length of m, yeah. Exactly, we got this now. Could also be written as 1 plus the length of, yeah. And we've defined it to be 0, so there we go. There it is. Right, let's implement sum. Right. Let's implement sum. We know that the sum of an empty list is 0. We write that down as a pattern. Wait, what time is it? It is lunchtime. How far are we? Yeah, let's go down to guards. All right, sum. We take number, a list of numbers, and we get a number out. Yes, exactly. That makes sense. If we have an empty list, we say that that is, the sum is 0, because what else would it be? And then we take a sum. All right, and we do exactly the same function, yeah, where we call the head added, the head plus the tail. Head plus, well, plus the sum of the tail. There we go. Take the head plus the sum of the tail. Nice. Yeah, that's pretty much exact the same thing we did before. We just replaced the one with... and we started caring about what the head was. Right, there's also a thing called patterns. Wait. Those are a handy way of breaking something up according to a pattern and binding it to names while still keeping a reference to the whole thing. You do that by putting a name and an at in front of a pattern. For instance, the pattern XS at... okay. This pattern will match exactly the same thing as this list, but you can easily get the whole list via XS instead of repeating yourself and typing this whole thing out. Again, here's a quick and dirty example. Alright, we have capital, the function that takes a string and returns a string. Right, if we get an empty string, then we say, oh, it's an empty string. Just like we did over here. We take capital and then we say all. Did all matter? No, all is just oh, right, we bind it. That's what we were talking about at the beginning of the stream, right? We bind it to all. So if we want to use whatever the thing is that we call the full of it as one whole thing, that's what we do. All right, the first letter of all is, wait, not the first letter. No, I don't think I got that at all. Let's read this again. Right, there are things called as patterns. Those are a handy way of breaking something up according to a pattern. Oh, right. No, not right. While still keeping a reference to the whole thing. So the whole thing is the whole list. Oh man. For instance, the pattern XS, that's a list, right? Where you have the first element, the second element, and the rest of the list. This will pattern match to exactly the same thing as the first pattern, but you can easily get the whole list via XS. Exactly, that's the whole list. All here is the whole list. Now I get it. This is the full list. X is just the head. Now I get it, yeah. Yeah, so this is the, yeah, we can, within this side, we can call the head, we can call the tail, we can call the entire list on the other side of the equal sign. That's why we have the pattern thing. Yeah, because if we wanted to call the full list, we would have to call, well, it seems fancy. Colgatinotab says, why not all X and then... Oh, because all cares about everything. All right, I can show that. All right. Oh shit, it's kind of... No, this time it worked. Weird. All right, we'll reload. Because it calls, within the function, we call the entire list. So we do care about what the list contains. No, shit. Wait. Oh, right. I was confused. Right, and then we call capital hello, right? See, the first letter of hello, see, it calls the entire thing. So we do care about the entire list. That's why we take all and then all of it. Because we care about hello and H. Oh, actually, they did it right here, yeah. The first capital of Dracula is Dracula. And since they call the entire thing, I mean, an equivalent way of doing this, or the same way of doing it, is that we could remove the all altogether. And then we could, instead of writing all here, we could just... Right. And that would be the same, right? Yeah, that is the same. So it's just a way, if you're writing long and convoluted functions, right? Or if you have... no, if you write functions that have a lot of variables, right? If you care about many elements in the list individually, but you also want to call the entire list in its entirety, right? If we would have like a super long list, right, we could create a list like this. Right, we could create a crazy list like this, and if we would use, right, now we have access to all these, the first, how many, like the first 10 or 15 elements of the list. We could call them all individually if we like, but here we couldn't call the entire list, right? We can't call the entire list if we want to. This is a way to call the entire list. Volgatino tab says makes sense. Yep. I don't know how often you want to do this, but this feels like such a thing where my mind just glances all over it and I will not remember this thing at all. And then when I end up in a situation where I actually need this, I'm gonna be super confused because I won't remember this at all, because it doesn't feel super useful, but it probably is more useful than I think. But that comes with experience, yeah. Normally we use patterns to avoid repeating ourselves when matching against a bigger pattern. We have to use the whole thing again in the function body. Yeah, exactly. One more thing, you can't use ++ in pattern matches. If you're tied to pattern match against xs plus ys, what would be in the first and what would be in the second list? It doesn't make much sense. It would make sense to match stuff against this or this, because of the nature of lists, you can't do that. Yeah, I can't. Wait, why not? Oh, right, because we don't know. Yeah, we would have to, right? If we wanted to do something like this, we would have to... Yeah, we would have to write a function where you take two lists. Yeah. Right, because this is a list and this is a list, right? So you would have to Right, over here you would call two lists separately. Because, yeah, that would be weird. Colgate on tab says I haven't used at all. Nice. Pun intended. I've just repeated the list when I needed like fool. No, I think that's fine. I think, right, if you don't end up in this situation very often, right? Hopefully you don't, right? If you don't end up in this madhouse, then using the at is just adding complexity. It reduces readability and it increases complexity, right? Usually, like it always is with computers, we can increase complexity to get more control. But increasing complexity needlessly is it's probably a good idea to avoid, right? If you don't really need this, you should probably avoid it. And write it the other way around. Yeah. Write it this way instead of, yeah, just add this. You could probably have, even if you needed the 10 first elements in a list, you could probably type them all out. Yeah. Yeah, so increasing complexity for the sake of complexity. That's actually, I learned that lesson from... no, I didn't learn it from, but that lesson got reiterated in Exapunk. Colgatino tab says, pun was intended. Nice. Nice. Alright, so, but that's it for today, and tomorrow we will continue with the guards. Those, we got hinted about the guards yesterday, I think? Yeah, yesterday. But tomorrow we will continue with the guards. Alright, so thanks for hanging out. Yeah, and have a good one. Yeah, see you next time. Cheers.